Electromagnetic induction was discovered by Michael Faraday on August 29, 1831. It is the phenomenon of the generation of electric current, electric field or electric polarization when a magnetic field changes over time or when a material medium moves in a magnetic field. Education on our planet gives an example of only one way of inducing electromotive force, when moving a conductor in a magnetic field. This method involves rotating a conducting frame in a magnetic field. The conductor crosses the magnetic field lines, causing a potential difference to arise at the ends of the conductor. This method is very old and was used in the Graham dynamo, and is used today in axial generators without a core with permanent magnets. Alternators and dynamos, where the phase wire is hidden in the slot of the anchor or stator core, work on the principle of induction of electromotive force when the magnetic field changes. Education does not disclose this method at all. The very first electric generator of Hippolyte Pixii in 1832 worked on the principle of changing the magnetic field. Its design is given as an example, without disclosing the mechanism of EMF induction at all. All turbo generators of power plants and small alternating current generators of gasoline generators have the principle of EMF when the magnetic field changes. But education claims that they have the principle of cutting wires with magnetic lines of magnetic flux. If we look at the drawing of a generator with a movable anchor, we can conditionally assume that this is a frame system that moves in a magnetic field. To demonstrate this type of induction of electromotive force in schools, a corresponding educational generator is used. We see turns laid out in the form of a frame, and no iron core. For a conductor moving in a magnetic field, the formula for calculating EMF is used, which is the product of the length of the conductor under the action of magnetic induction, by the corresponding speed of the conductor, multiplied by the coefficient of the angle at which the magnetic induction vector is directed to the conductor. To fulfill this expression, an important condition is the magnitude of magnetic induction at the point of contact with the conductor. Let us remember this important point.
Earlier I showed a handheld electromagnetic generator with a movable anchor, which is used for demonstration purposes. The anchor of the generator has a winding to create EMF and is used in two positions, as an alternating current generator and as a dynamo machine. This type of generator is related to the simplest electromagnetic generators with cores. In textbooks about typical synchronous generators, this particular version of the magnetic system is given, only with a rotating magnetic rotor. In these generators, the electromotive force is calculated using the transformer formula of EMF. This formula completely coincides with the phenomenon of changing the anapole moment in a closed magneto circuit. To understand the difference in typical synchronous electromagnetic generators, it is necessary to clearly distinguish what is the source of magnetic flux, and how it affects the change in density and direction of magnetic flux in a magnetic closed circuit, magnetic anapole. You see two main types. The first and main one is when the magnetic rotor rotates, and the winding and core, in which the magnetic flux changes, are static. The second type is most associated with magnetosystems or DC generators. In it, the anchor with windings rotates in a constant magnetic field. To conduct a real experiment to determine the method of inducing electromotive force when rotating an anchor with windings in a magnetic field, a model of this educational hand generator was purchased. To conduct the experiment correctly, the model was equipped with a system for determining the anchor position using an Arduino line sensor. A disc with a white-black stripe is installed on the anchor shaft, to which the line sensor is oriented. The white stripe is a logical 1, the black stripe is a logical 0. The blue beam of the oscilloscope is connected to the output of the line registration sensor from the Arduino. We can observe and record the position of the anchor on the computer screen, to which the oscilloscope monitor is connected. The yellow beam is connected to the contacts of the bulb to record the electromotive force. The permanent magnet excitation system consists of two permanent magnets connected by a metal bridge approximately 5 mm thick. We will take these parameters into account for further calculations. If we look at the anchor poles and the excitation magnetic system poles, we will see a very large 5 mm air gap between them. The armature wires have an even greater distance to the excitation magnetic poles. We rotate the anchor of our school generator, we get synchronized graphs of electromotive force and anchor position, during the generation of electrical power when heating the light bulb. The data obtained surprised me a little, since the maximum EMF was at the moment of complete opening of the magnetic circuit. If we make a graph and superimpose the obtained data on the rotor position, having made the corresponding school drawing of the Sagnet system, we will receive indirect confirmation that the magnetic lines of force cut the conductor. Perhaps it is the position of the anchor that forces the formation to this conclusion. Let us recall the formula for calculating the electromotive force for this moment. At the point of contact of the wire and the magnetic flux, there must be a corresponding value of magnetic induction. This will be enough to confirm or refute the constant of educational physics. In the FEMM program, I modeled a magnetic system to determine the value of magnetic induction at a point of the anchor winding conductor. The result showed a technical zero of magnetic induction in the zone of the supposed intersection of the magnetic lines of the conductor. The program indicated the fulfillment of Ohm's law for magnetic circuits, that the magnetic flux always goes along the shortest path and the least magnetic resistance through the core poles. The maximum closure of the magnetic flux at the moment when the EMF is zero. Let's analyze how the EMF is formed in this generator. When modeling the magnetization of the anchor, according to the current strength in the winding, it turns out that the magnetic flux of the anchor at the position of complete closure of the magnetic circuit is zero. When the anchor leaves this position, the magnetic flux of the excitation magnetizes the anchor. The EMF induction appears in the winding, only in those wires that are inside the magnetic flux. Upon reaching the anchor position, when the magnetic flux should be opened, the magnetic flux in the anchor is maximum, since it is amplified by the magnetic flux from the phase winding. With further closure of the magnetic circuit, the anchor pole has the same polarity as the pole of the excitation system. The excitation system begins to demagnetize the anchor, while the EMF in the winding decreases. When the anchor reaches the position of complete closure of the magnetic circuit, it will be demagnetized. Further movement of the anchor will be associated with magnetization from the excitation system with an increase in magnetization from the phase current. All these actions completely coincide with the synchronous change of electromotive force. Let's calculate the electromotive force using two formulas that are in physics textbooks. Using the formula for a conductor that moves in a magnetic field, we have obtained possible readings of magnetic induction in the conductor zone at the maximum EMF level. Using the transformer EMF formula, we will take the maximum magnetic induction calculated at the place where all the magnetic lines pass. This is a metal jumper connecting two permanent magnets. We got very different results. For the method of cutting the magnetic lines of the conductor less than 1 volt for the entire winding. This parameter can be considered zero, since it will not light our small bulb in the load. For the system of changing the anapole moment, calculated by the transformer formula of EMF, the result of 9 volts was obtained, which completely coincides with the readings of the voltmeter when measuring the voltage at idle speed of the generator. Thus, the constant of induction EMF, for studying the work of a synchronous alternating current generator, which is offered by modern education, is erroneous or intentionally changed. This feature is not important for 99% of the world's population. The construction of such electromechanical machines is carried out by a few design engineers who know this. It is for this reason that physicists call the formula of the transformer EMF an engineering formula, since they cannot explain its work. We have explained the work of this formula literally. The next constant of physics that misleads humanity is the assertion that an electromagnetic mechanical generator is a converter that converts mechanical energy into electrical energy. There is no direct physical connection from the mechanical force of rotation of the magnetic rotor to the induction of EMF in the phase wires of the alternator. Mechanical force is a condition for rotation and for overcoming the magnetic interaction of the magnetic rotor and the stator of the machine. The cause of the induction of electromotive force is the magnetic field of the rotor that rotates. Are the direct costs of generating magnetic flux equal to the output power when generating electricity? For turbogenerators, the excitation power is approximately 0.5% to 3% of the generator power. Let us ask ourselves whether it is possible to rotate magnetic poles with a static rotor core. First of all, let's look at the DC motor. The excitation is in the stator, and the anchor has a ring winding commutated through brushes and collector lamellas. This principle of the electric motor has hardly changed since the 19th century. The polarization of the anchor, through the excitation with direct current, occurs in such a way that the magnetic poles are constantly pushed out and pulled into the magnetic poles of the stator. If you look at the position of the magnetic poles of the anchor, they practically do not change position, only the anchor core rotates around the axis. You can make it yourself, a generator without mechanical rotation of the anchor. 1. Find an anchor from a DC motor, with a two-pole excitation orientation. The winding must have a sufficient number of turns. It is better to use one from a motor with a constant excitation of the field from permanent magnets or an electric motor with self-excitation for 110 or 220 V. There, the anchor winding is designed for less resistance, but has a sufficient number of turns. 2. Find a stator with slots so that your anchor fits tightly into the stator without a gap, or with a minimum gap. Provide a uniform gap between the stator and anchor bars. 3. Wind the stator winding for a three-phase generator system with two-pole rotor excitation. I think a simple winding mechanism is available online. If you already have a ready-made winding from a three-phase motor for test runs, use it, but for a generator this is not the best option. Connect the stator winding through a three-phase diode bridge to an adjustable laboratory load for measurements. 4. Make a device for organizing the rotation of the contact brushes around the collector lamellas. 5. Assemble the circuit without closing in a ring version. 6. Start without turning on the load. Select the optimal speed of rotation of the brushes around the collector at the possible maximum allowable excitation current. Measure the current at startup and in operation. 7. Connect a voltmeter, or even better an oscilloscope, to the terminals in front of the diode bridge. Measure the maximum EMF. Change the speed of rotation of the brushes and watch how the frequency and EMF change. 8. Connect the load in different modes, make the appropriate measurements. Excitation current and EMF level, current in the load. If you did everything correctly, you will have a current drop in the excitation circuit when the load is connected. You have generation. Then all that remains is to calculate the excitation windings and stator windings to obtain not a test verification model, but a design useful for generation. Start the era of generators without physical rotation of the magnetic rotor today. Don't wait, the energy lobby does not benefit from you generating electricity yourself. You can learn more about this and much more on my Patreon channel. Discover a lot of interesting things. Another interesting material is being prepared, stay tuned.